Come back. Problem 6. Integral 2 secant squared x tan x. This is a straightforward question. Integral 2 secant squared x tan x. Substitute u equals tan x. Then du equals secant squared dx. You see? So integral 2 secant squared x tan x will be equal to 2u du. Integral of 2u du is u squared plus c. U being tan x, it is tan squared x plus c. Constant of integration. Next, integral of 9 tan to the power 3 2x secant to the power 5 2x dx. Notice the arguments are the same, and that is very important. All right. So, because these are both odd powers, take one power from each away. So I get secant 2x aside, tan 2x aside, and the powers both become even. This is important because now you can substitute u equals secant 2x. Its derivative du is twice of secant 2x tan 2x dx. So that's where secant 2x tan 2x dx will be. What do I do with that 2? You see in a minute. So integral 9 tan power 3 2x secant power 5 2x dx is integral 9. So you removed a power of tan, you removed a power of secant. So you are left with integral 9 tan squared 2x secant to the power 4 2x secant 2x tan 2x. Now notice the next line is essentially the same, except I have divided by 2 and multiplied a 2. Why did I multiply that 2? Because of this 2. Okay, chain rule demands an extra 2. So 9 over 2 tan squared 2x and 2 secant 2x tan 2x. That's what happens. Now tan squared 2x is secant squared 2x minus 1. So 9 over 2 u squared minus 1 u to the power 4, u being secant 2x. All of this along with the 2 is du. Get the 9 by 2 outside, distribute the u to the 4th power. You have 9 by 2 integral u to the 6th power minus u to the 4th power du. When you take integration, that's a constant, u to the 7th power over 7 minus u to the 5th power over 5 plus c. U being secant 2x, we just simply resubstitute. Don't forget, constant of integration is on the side. Do not multiply 9 by 2 to the constant of integration. No harm done, but web work will complain because 9/2 constant is some other constant. They just want you to write c. All right. So let's write the solution down. 9 by 2 parenthesis secant to the 7th power of 2x over 7 minus secant to the 5th power of 2x over 5. Don't forget to close the parenthesis. Add a constant of integration. So that's correct. Good. Next, definite integral 0 to pi by 4 10 secant to the 4th power x tan to the 4th power x. They are both even powers. So what do? We set u equals tan x, then du will be secant squared x. So that's very good. I have secant to the 4th power. I split it as secant to the 2nd power and secant to the 2nd power. Secant to the 2nd power is nothing but 1 plus tan to the 2nd power. So I have an entire expression in u and du. So integral 10 secant to the 4th power x tan to the 4th power x dx is integral 10 1 plus u squared times u to the 4 du. Get distribute the u to the fourth. 10 is outside. Integral of u to the fourth, integral of u to the sixth, plus a constant of integration. Do not forget to resubstitute. U is tan x. So the final answer is tan to the fifth power x, 10 parenthesis tan to the fifth power of x whole over 5 plus tan to the, oops, I'm sorry, this was definite integral. So did I not calculate? Yeah, here we go. Definite integral. You need to take this. You don't need constant of integration anymore. Evaluate your expression here, trigonometric expression. Evaluate at the upper limit, subtract, evaluate at the lower limit. 0 is easy because tan at 0 is 0. Pi by 4 is also easy because tan of pi by 4 is 1. So all that comes down to 10, 1 by 5 plus 1 by 7. Tan 1 over 5 plus 1 over 7. Okay, let's check. It's correct. Next problem. Find the area of the region bounded by curves y equals sine x, y equals sine cubed x between 0 and pi by 2. Area of the curve, that's a nice one. So between 0 and pi by 2. So here is sine. The curve in blue is sine, whereas the curve in red is sine to the third power. So notice they meet at pi over 2. They both have height 1. They meet at 0. They meet at negative pi over 2. But we don't need this. We need only between x between 0 and pi over 2. Okay? Between 0 and pi. So the question is to find this area. How do you find this area? This is something we learned long ago in this particular course. In area under the blue curve minus area under the red curve from 0 to pi over 2. So it is a definite integral, integral 0 to pi over 2. The top curve is sine minus the bottom curve is sine to the power 3. Integral of sine is simply negative cosine x plus constant of integration. Integral, definite integral sine to the power 3 is this we have seen in our class already so far in these videos. It's negative cosine x plus cosine cubed x over 3 plus a constant of integration. So the definite integral 0 to pi by 2 integral sine minus sine cubed x will be integral of the first, that's negative cosine x, minus integral of the second, which is all of this. You don't need constant, and you are going to take the difference, integral of the first minus integral of the second. The first minus second in parenthesis, limits 0 to pi by 2. But notice these two make it positive and that's a negative. So cosine is going to disappear. All I'm going to be left with is negative cosine cubed x over 3. Evaluate it at pi by 2 and evaluate it at 0. Cosine at pi by 2 is 0. Cosine at 0 is a 1. There is a negative from before, from the expression here, and negative from the difference of the limits. So in all, positive 1/3. That's your area between the curve, between the two curves. Okay. Last problem, find the volume of the solid obtained by rotating the region bounded by the curve y equals tan squared x between x equals pi over 4, x equals 0 and y equals 0. So let's look at that. You are going to rotate it about the x-axis. Aha. So the red curve here is the curve y equals tan squared x. It actually goes on. You have a vertical asymptote at pi over 2, but we stop at pi over 4. So at pi over 4, between x equals pi over 4, x equals 0, y equals 0. X equals 0 is this line segment. y equals 0, that's y equals 0, then x equals pi over 4 is this line segment, and there is x equals 0. Okay, you don't need all of that. All you need is this region between the curve, this line segment and this line segment, and you're going to rotate it about the x-axis. So if I'm going to rotate it about the x-axis, I'm going to take integration horizontally from 0 to pi by 4. So we are looking at it as shells, cylindrical shells, if you remember. So dx is going to be the thickness of each shell, and the radius is going to be given by y. Radius is this distance, right? Because you're rotating like this, you're going to have radius is a vertical radius, that is y. So pi y squared. Y itself is tan squared. Pi tan squared squared dx. So this is the integral that you need to calculate. This is integral tan to the fourth power. But integral tan to the fourth power we have already done so far in our notes. Integral of tan to the fourth power is tan to the third power x over 3 minus tan x plus a constant of integration. I'm going to multiply all of that by pi and evaluate this expression between the limits 0 and pi by 4. 0 is easy because all these are 0 at 0. At pi over 4, tan is 1. This is pi over 4. So you have pi times 1/3 minus 1 plus pi over 4 and nothing more. Okay. So simplifying this, 1/3 minus 1 is negative 2/3. So that's your final answer. Let's go. Pi bracket pi over 4 minus 2 over 3. Let's check. Alright, so this completes our problems from section 7-2. We'll continue next section in our next video. Until then, bye.